All right. So these are some advanced concepts that we've touched on some of the groundwork for this before. Let's move on. So first, a bit of history. First, I want to just sort of get into a really, so let me just stop for 1 second and pause. Years and years and years ago, before my time actually at BCIT, this was a whole lecture. There was a whole course almost on the history of television. I'm not sure why. I dropped that. I did it first year or two. I did a lecture on history, and then I basically made it 3 or 4 slides because you know what? Time's moving forward. We can look at the past as far as how it affects how we are today, and that's what we'll talk about now. But there's not much point unless you want to take a different course on understanding the history of TV and video and film. So, let me just get some water and start here. I'll just do a fresh take. Excuse me. Okay. So let's discuss a bit of history. Black and white television. So as you can see on this wonderful slide, standards for North America were 525 horizontal lines of resolution at 30 frames a second. So the only thing I need to say that's not on this slide is that there was a group called NTSC, the National Television Standards Committee. They were formed in 1940, I think it was 39 or 40, because in the United States, surprise, surprise, there were a number of competing standards already. Television itself as a technology by 1940 was about 15 years old, somewhere in the mid 1920s. The sort of the idea of television crystallized, and the technology made it possible to transmit pictures. Practically speaking, there were earlier efforts, etc. So of course, as is always the case, when everything new comes along, everyone struggles and fights to have the one that wins. And so everyone comes out with their own competing standard and tries to improve this, that, and the other thing. So when I say standards, kind of almost with a capital S, in North America, there was a group called the National Television Standards Committee. They were formed in 1940 to eliminate a lot of these incompatible sets, because what was happening was broadcasters could only broadcast to people with one particular type of television set. And of course, that meant if you wanted to watch multiple channels, you had to have different television sets. So that was crazy. Although that still exists today, right? I mean, you can see all kinds of things today that are crazy, and we can talk about that later on. So they settled on 525 lines of resolution at 30 frames a second. So one of the reasons they decided on the number of lines was with the technology of the day, the way the picture was constructed, and I'll talk about that next. It was constructed basically line by line from top to bottom. By the time they got to 525 lines, the lines at the top of the screen were starting to go dark. And this is because electrons were hitting the screen. They were stimulating some chemicals. They would glow momentarily and then eventually fade. And so the combination of 525 lines and 30 frames a second allowed the picture to stay up on the screen long enough and not flicker, right? So that was kind of the basis. It's sort of the same idea as the film frame rates. Film was chosen not because of the fading factor, the frame rate, pardon me, but because, of course, that below 24 frames a second, people could start to see that flicker. The other reason they chose 30 frames a second is because it was a handy number. They could have chosen numbers around that number, but because television was based on electricity and electricity runs at 60 cycles, they could divide that 60 in half and get a nice even frame rate, right? So everything was wonderful for a while. Oh, and then there we go. So notice that when I'm talking about it, I talk about lines. There were no pixels in early television. Pixels came along later. Television screens were designed and built with a system that scanned line by line. Other countries had other standards. It's only fair to mention that the UK, and now we're talking black and white, by the way. This is pre-color. This is why some of these numbers are kind of weird. The UK had 405 lines at 25 frames. France had 819 lines at one point at 25 frames, and Poland had 441 lines at 25 frames, etc. So there were all kinds of standards all over the world. So I'm really only focusing on North America when I talk about standards. We'll touch on some of the other ones later. The other bit about television early on was there was only brightness information. There was nothing else, right? The part of the screen was either brighter or darker, and that's really all you had to measure and all you had to transmit. So it was a pretty straightforward signal. So here's that you can see this is my cheesy illustration of the lines, what the lines would look like. Of course, they're much, much thinner than that. You'd never see them. You know, if this image, will go back a frame, if this image that you're seeing here was a television image, it isn't, it's a graphic. But if it was, it would look much like this. You wouldn't see these scan lines. This look, and you see this now in a lot of movies and stuff and TV shows, they impose these lines to sort of signal to the viewer that this is old-timey TV. But as someone, I can tell you, as someone who lived through the era of old-timey TV, you didn't see these scan lines at all. The image is quite clear. I mean, the only way you would see them is if you got up in front of your TV, you know, within 2 or 3 feet. You might start to see the lines. Even closer than that, you might start to see the lines. But even then, they were very, very thin. But I've exaggerated here just for the sake of illustration. So anyway, so in the beginning, television images were made up of lines that were built up one at a time, sort of laid one on top of the other, or up and down, sorry, the screen. But the problem was even that required a big amount of bandwidth. Now the bandwidth back in the day wasn't data bandwidth because it was analog, but the bandwidth was the width literally of the radio band, right? So that's where the term bandwidth comes from. So the television is broadcast on a radio signal, or was. I suppose digitally it still is. And the radio signal was called a band, and that band had a certain amount of space, literal space, you know, the size of the wavelength. Is that right? Yeah, the amplitude, I'm sorry, the amplitude of the wave, the height, and size of the wavelength limited the size of the data that you could travel along in analog. So they had to figure out a way to cut the picture data down. And what they came up with was, oh, that was interesting. Oh, I see. Okay. What they came up with was, but they divided the frame in half. So what I've done in this illustration is every other line is lighter than every other line. You'll notice that the even numbered lines are dark and the odd numbered lines are lighter in my picture that I've made. And that's what they did. They divided the picture into these different, what they were called fields. And they were half of the picture, 212 and a half lines, right? Every other line. And they were basically put, so one was odd, so 1, 3, 5. So if we look at this image, we see the light color ones as 1, 3, 5, 7, 9, all the way up to 525, and then 2, 4, 6, 8, right? And that's how that was done. And I'm going to stop just for a second, the share, and show you me, and say that if you think of it as interlacing, you have half the picture and half the picture, and you literally put them together like this. So you have the even lines, the odd lines, the even lines, the odd lines, right? And that's how it was done. Let's go back to sharing. Okay, so. Oh. So the two fields together made one frame, right? This was called interlaced video. This is different from progressive, and we'll get into that a little bit later, but progressive is essentially the entire frame at once from the first line to the last line. And that's because modern technology allows it, but old technology didn't allow that to happen because of the restrictions of bandwidth. What they did though, in order to have it appear at 30 frames a second, they had to double the field rate. Okay, and this is where people's heads can sometimes hurt. What's happening when you double the field rate is you show these halves of the image, and I unfortunately didn't think of designing a picture showing only one half. But if you think of all the light bands and then all the dark bands as two separate frames and a space between them with nothing in it, they would show those at 60 times a second, so that when you lace them together, you'd get two of them together every 30th of a second, right? And that's because of persistence of vision. Because you could show them so fast, our brain could see them merge together 30 times a second. All right. I hope that makes sense. So the field rate is not the frame rate. You don't have a full frame. And the terminology is important because a full frame is only considered to be an entire, remember I used the word raster last week, an entire image complete. Half the image is not a frame. And in the case of interlace, you could call it half a frame, but they use the term field for those every other lines, all right? So after that came color, and that would have been 1950-ish, 54, 5-ish. And so here's the thing, because America was so, well, America was in a kind of interesting pickle here with television development. First off, they were early adopters. They were like I said, back in the 1920s. I mean, this is not to discount other countries that did experimentation and had, like I said before, the French, the Polish, they all had systems, but they didn't have the money. They didn't have, well, there was a lot of reasons. I mean, there was the war came along and devastated a lot of countries. You know, Britain, for example, during World War II, shut off all television broadcasting in 1939 because they wanted to dedicate all their effort to the war, and also because they thought the television transmitters might attract bomber aircraft. So I actually visited many years ago a place called the Alexandria Palace in London. It's called the Ali Pali because the British do those kinds of things. And at the Ali Pali is the first television transmitter in Europe. And in fact, they argued it might be the first one in the world, but let them fight about that somewhere else. Anyway, I digress. So North American television had an issue, and that was they had already sold lots of TVs. By 1954-ish, 5-ish, and here, let me just, because it's weird me looking at this slideshow. Let me just stop the share. You can see me for a second. So the trick is that television became really popular. So the number one, what they would have called the killer app back in 1951, 2, 3, 4 for television was, anybody guess? What was the show that made everybody buy televisions? Wrestling. I'm not kidding you. Wrestling, and the second, number 2 was bowling. Oh no, it wasn't Mickey Mouse. This is long before Mickey Mouse. This was when television was sort of experimental. And so wrestling sold television sets to bars. I'm not kidding you. So bars would buy, because wrestling was kind of a local event. There was no such thing as kind of a national wrestling organization. It was all done, every city, New York, Toronto, Philadelphia, Boston, they all had their own little wrestling circuit. And so that, the men would go down to the bar and the TV would be up on the wall, hanging on the wall, and they would have wrestling on there. And then the next one was bowling, of all things. Bowling, because bowling was easy to do for television. It was indoors. You could light it any way you needed to. You could put the cameras anywhere on the bowling alley, even in an adjacent alley, so you could see the bowler in profile. There's all kinds of reasons for bowling. So bowling became, and this is, again, I'm talking late 40s, early 50s. So the story, the reason I'm saying that at all is they sold a lot of television sets. And the fear was that if they went color, they would have to go to a different standard and all the TV sets would stop working. Well, they would keep working, but they wouldn't get the color signals. That was basically the problem. So they had to develop a system that was compatible. So let's go back to the story at hand. Oh, and I didn't share, did I? No, because share screen, share screen, share screen. Why can't this be done in one click? Current. Okay. So they developed, they developed a color system in North America that ran at the same rate and used the same standards as black and white, and they overlaid the color on that signal. And that was called, and don't worry about this, remembering this, but it was called a color under system. And what that meant was the black and white system was there, and then underneath that ran the color system, and they ran in parallel, right? Now, the only difference, and the only reason this is even worth talking about now, is they had to adjust the black and white signal ever so slightly to make room for the color data. And what they did, there was a whole bunch of ways they could have done it, but what they chose to do in the end was slow down the frame rate by 1%. Or in fact, I think it's 100th. I think that's actually wrong. I think it's 1/100th of a percent. And what that meant was they slowed it down by 0.3 frames per second, right? So why do we care about that at all? Well, because it allowed more time for the color information. And it also meant that the television sets were so, what's the word I want? Sloppy is a bad word. They were so imprecise that you could adjust the frame rate slightly and the TV set wouldn't notice. You could move I bet you could probably move one whole frame per second one way or the other, and those old TVs probably would have still showed the picture just fine. And humans wouldn't notice a difference. I mean, you wouldn't notice between 29 and 31 frames, right? So they made that adjustment. The TVs still worked, but now we had what was called a non-integer frame rate. And all that means is the frame rate wasn't a whole number, okay? So with the frame rate, yeah, now I've got it proper here, 0.01%, 1/100th slower, that's what it was. It's now 2997. And that's a number you might be familiar with. You might have struggled with it already. It's not an even 30. The frame counting method had to change, and we had to invent something called drop frame timecode when timecode was invented. Timecode wasn't invented until much, much later, because for one thing, when the color system came in, there was really no videotape. There was no way to record the television image electronically. You could record it on film, and there was something called kinescopes, which were film recordings of television, but there was no electronic recording until this, practically speaking, until the early 60s. And when the television electronic recording came along, which also known as videotape, that's when they had to develop time code so they could edit. They had to mark the frames. The first thing they realized after they invented videotape was, how do you know which frame is which if you don't mark them? And they marked them electronically with numbers. They invented time code, but the time code couldn't be even, right? And we'll talk about that later today when we talk about time code. I just wanted to mention this. So the two takeaways of this portion of the lecture is that we have interlace. We're still living with interlace, right? You still know about 60i and 60p and 30i and all that stuff. That's all an artifact, if you want. That's all a cause by this North American standard. There are not these problems in other parts of the world where they don't have NTSC, right? There's no such thing as a PAL interlace, for example. PAL is 25 frames even or 50 frames in HD. Done. Simple, right? But we're still living with interlace. And I was hoping, I was part of the transition at CBC back in the 90s from analog to digital. And we were hoping then that things like drop frame and interlace would go away. And here we are almost 20 years later, and it's still not gone. You know, you're still looking at the 30i, 60i, 60p, 2997, you know, all these other 2354, and all those other weird frame rates, thanks to this. So that's why we got those things. That's my little history lesson out of the way. We shall never talk about history in that same detail again. All right. So, topic change. Let's talk about color. In fact, stop share. No, you know what? Don't stop share. I'll just pause for a second here. I'll do a little bit of, this is to help me edit if I have to edit. Okay, color. Color and video. So remember I said color was invented. Television uses what's called an additive color system. Because television images and computer images and a number of other types of images are built up using light, the only way to make light change colors, if you will, is to add other frequencies of light together, right? We have an additive color system in television. It's RGB, red, green, and blue, pretty straightforward, right? There is a subtractive color system, and this is where people can get confused and can also run into traps. The subtractive color system is used in things like printing or painting or dyeing of fabrics. So the subtractive color system is a different color system, and it has different primary colors. So we talk about the primary colors of RGB, red, green, and blue. And the system is named after the primary colors, and as is the subtractive color system. But the primary colors in that are CM and Y, cyan, magenta, and yellow. And they mix to make black. And you have what's called the CMYK color system. So the reason that there's a K in CMYK is because inks are not perfect, dyes are not perfect, paint isn't perfect. And if you mix the three primaries together, cyan, magenta, and black at equal measure, you don't get black, you get kind of a brown. And that's just a limitation of the physics of substances. So they introduced what's called a K or a key, and the key is really just black, okay? So in order to get a true black, you have to add it as a black pigment. That's why CMYK is a 4-color system and RGB is only a 3-color system. In RGB, you can get all colors with just 3 primaries. In CMYK, you need 4. All right. So just a quick summary of the differences. An additive color system, you mix colors to make white. More colors mean more brightness. So more colors you mix in, the brighter the signal gets and the image gets. And the maximum color value in the additive system is white. That means all colors mixed together will give you white. That's what we mean by maximum value. The subtractive color system, you mix colors to get black. More colors mean less brightness, because as you add pigments, less color is reflected back to your eye, right? Because the pigments absorb, we'll try that again. Pigments absorb light, right? So the subtractive color system is really a reflective color system. Light hits the pigment and the pigment absorbs a color and reflects the rest back to you, or vice versa. And as a result, more color means less light reflected back, less brightness. Therefore, the maximum color value in a subtractive color system, when you add all the colors together, equals black or no reflection at all. And as I explained before, we have to add K because of the weakness of physics of substances. If substances such as color molecules, chemicals that make up colors and such were perfect, then you wouldn't need K. Everything would mix together to make a perfect black. But the reality is that doesn't happen. That's just the world. Okay. So again, just to underline the differences, the additive color system starts with black, and as you add colors, moves towards white. And the primary color system starts with, or pardon me, the subtractive color system starts with white, or in this case, paper color. That's the other difference, by the way, with subtractive color, is that in additive color, there is no light, which means it's an absence of light, which means it's black automatically. In a subtractive color, when there's no color, the color that remains is really the color of the background. So you assume it's white, but of course, you know for a fact you can print on different colored paper, you can paint on different colored walls. So the subtractive color system has a few more wrinkles in it for designers, but we won't get into that here. All right. The other thing about additive color is you can add the colors together to get the subtractive color primaries, and these are the complementary colors in additive color. So I hope this isn't too confusing. So remember, the primaries are R, G, and B, red, green, and blue. If you mix red and blue together, you get magenta. Well, magenta happens to be the subtractive color primary, right? And also, if you mix red and green together, you will get magenta, right? And if you mix green and blue, you get cyan. Okay. Now, it looks yellow on this screen, that green and red mix, and I'm not quite sure why. I just noticed that, actually. G and B, cyan, R and B. Oh no, R and B is magenta. I'm sorry. That's my bad. We'll try that again. Adding red and green light together makes yellow. Adding red and blue, you know what it is? I'm not reading this in order. Green and blue is cyan, and red and blue is magenta. That's what's happening. Okay, a little Mike Lexia there for the early morning. Okay, moving on. And I've already said this about subtractive color. It combines pigments that absorb light, and the remaining, what we see, is reflected off. Whatever is not absorbed by the pigment is reflected back at our eyes. That's subtractive color. All right. So the other thing to remember too is when you're looking at additive color systems, when you're looking at the colored image, you're looking at the light. When you're looking at a subtractive color image, you're looking at the reflection of the light. Okay, that's another key difference. All right. Here's the primaries and what they make, and you'll notice that the CMY, because those are the three primaries, the K is the center, the black. The CMY make the RGB primaries when they're mixed together, right? CY green, MY red, CM blue. So if you mix pigments, if you mix cyan and magenta together, you'll get a blue pigment. If you mix cyan and yellow together, you'll get a green pigment, right? Okay. So the other thing about RGB color means you need to have three television signals, three video signals. RGB video uses a separation of red, green, and blue. And so did early film, by the way. Early Technicolor film ran on what's called a 3-strip color system. And that was each strip of film had one color that was sensitive to only. And it ran, I can't remember the movie that I saw, but they basically ran 3 strips of film, one after the other, all at the same time. Stacked on top of each other inside the camera. So 3 reels of film to get one color product. That was improved later on with chemicals and technology, but early film was a 3-color system. Video still is, all right? Video used to have 3 sensors, and now we've pretty much standardized on 1 sensor, although you can still buy 3 sensor cameras. I don't know if we talk about that when we talk about cameras, but we'll put that aside for now. Most cameras nowadays are a single sensor. So you have to filter the light. You got to split it some way, right? And again, we'll talk about some of this splitting and filtering when we talk about sensors later on this month, next month, soon. But understand that the important fact here is you have to filter the light. You've got to separate the colors somewhere in the process. They use formulas based on voltages, just for a matter of interest. And again, we'll talk about this in detail with sensors, but all images land on a sensor as an analog signal, and that analog signal is converted within the camera. So every digital camera is going to be capturing well, not capturing. Yeah, every digital camera captures analog and processes it into digital. As far as I know. I say that generally, and then you can probably Google and find out otherwise. All right. How it's done, that changes from camera to camera. That's part of the secret sauce. We'll talk a little bit about how some of the stuff is done in sensors, but the secret sauce of camera manufacturers is we do it a better way. We do it a different way. The same with monitors. We'll talk about monitors as well. As long as you resolve the picture in an RGB image, it doesn't matter how. So monitor manufacturers are free to do it any way they like. All right. Oh. Yeah, and I've said this already, 3 sensor chips. In some cameras, most cameras use a single sensor chip. All right. I'm going to stop share for a second, take a breather, see if there's any questions, because that was a lot. I've got to find a better way to do this, because I keep losing the chat. When you share the screen, you lose the chat, which is really weird. I wonder if I should log in elsewhere here. I'm going to try this. Anyway, any questions about that before I carry on? Oh, I guess I could stop the recording or pause, resume. Okay, so gamut and color space. This is the next section. There we go. So one thing to keep in mind is that video cannot reproduce all the colors. So what you're seeing here, and we'll go into this in a little more detail in a minute, what you're seeing with that sort of arch shape with the numbers attached to it is something called a CIE diagram. And what the CIE diagram is a description of human perception. What the triangle that you're seeing in the middle of that black field is, that is the color space for the old analog television system, the SMPTE color gamut. And gamut we'll discuss in a minute. But basically, that triangle are the only colors that analog TV could reproduce. So even though the humans could see that big black sort of arch shape, so everything inside that arch, it looks a bit like the toe of a shoe, or, it just has that kind of triangle with a weird floppy end, or like someone's cut the end off a baguette. It's got that kind of shape to it. Well, all that stuff inside those lines should be visible by humans, or is visible by humans. But the system that we're using in analog TV could only see what's in that triangle, right? So you can see there's lots of colors that television just didn't, and video did not produce. This isn't just television as well. I mean, these same kind of triangles exist for computers, right? There's all kinds of RGB color spaces. Anyone that's gone into Photoshop or Premiere and played with the color space settings, I forget what Adobe calls it, but I think it's color space, I'm not sure, or color system. Or if you go to your Mac or PC and you want to adjust the display color systems, you'll get this pull down menu of all these different names. Well, that's what they represent, is what kind of a triangle do you get, all right? So the space that's visible, that colored triangle, is called the color space. The color space is a subset of all visible colors. Now, that's not a strict definition because it's a set. That means the color space of all visible colors is also a color space, right? So if we look at this diagram in a different way, here we go. So here's the diagram with all the colors filled in. I'll go back in a second. This diagram is the complete diagram. So everything that's colored is everything that we can see as humans. The reason that it's kind of that weird shape is that you can see that humans are more sensitive to some colors than others. So this shape is specifically designed to indicate that humans are more sensitive, for example, to green than almost any other color, second only to blue, or pardon me, blue is second only to green, and then red, and then the other colors in decreasing sensitivity. And that's represented because green has the biggest area, blue has the next largest area, red has the third largest area, and then the purples and the yellows and the pinks and whatever, right? So that is the human color space. Okay, it's why it's called color space. I don't really know why it's not called color area or color whatever. Who knows? But they decided on the term color space. So color space is also here we go. Hang on. Where were we? Color space is also defined as areas within that giant area, and they're smaller. And by definition, the color spaces that are not the entire area are fewer colors than we can see. They're not as sensitive as human eyes, right? Now, some color spaces, and I don't have an example, but I wish I did. For example, if you look at the color space of what a dog could see, the triangle would actually go outside the lines because dogs can see colors we don't see. Birds are the same, right? They see colors we don't see, but also dogs don't see colors we do see. So I'm glad I don't have these shapes because they would be confusing. We're only going to talk about humans in our experience because the only people I know at the moment that make video and film are humans. I haven't yet met an animal that does a good directing job or good editing, but you know, who knows one day. So that's what the color space is, and that's the color space, like I said, that triangle we're looking at right now, that colored triangle, is the color space of standard definition analog TV. Okay, so now we're going to back up a step and talk about the diagram in a bit more detail. It's called the chromacity diagram. That's how you pronounce that word, by the way, not chromacity. It's not a place to visit, although I guess Chroma City would be kind of a cool place to go, or Chromat City. The chromacity diagram measures the color. Chroma is the word for color in, I think, Latin. And so this diagram illustrates the colorness, if you will. It's also known as CIE 1931 because that's the year it was not discovered but developed. It has a whole bunch of this particular illustration you're seeing here has a whole bunch of notes on it, and this diagram is handy because you can use it for all kinds of things. Here, someone's using it for talking about color temperature. All these numbers that are inside the triangle, and I'm pointing at the screen like you can see me. I'll use the cursor. You can, this little tiny cursor, I should get a bigger cursor. All these numbers inside here are color temperatures, and we'll talk about color temperature another time, but that's what this particular diagram right here in front of you is being used for, but it has all kinds of other uses. You've seen it, if you've done any color correction, you might have already seen it in your color correction layout for DaVinci or Premiere. I think they have an option to show you this diagram. Okay, and as I said before, this shape, as is the colors, all colors available to humans. All right. So here's one of the weirdnesses about RGB color is that the colors don't really have names. They have values, and those values are numeric. The colors that you hear about that have names are typically pigments. Like if you go to the hardware store and you go to the paint section and you'll see a wall of like 1,000 different paint chips, every one of those colors on those paint chips, every single one has a name. That's because pigmented colors are easier to name. I don't know why. We don't name colors in RGB. We typically talk about red, green, and blue. And then we talk about the cyan, magenta, yellow, complementary colors. And after that, we stop using names. We start talking about values, okay? So that's just a sort of a side note. What does CIE stand for? It stands for Commission Internationale de l'Éclairage. Oh man, that is a mouthful every time. And it's because that was a French discovery, French invention, hence the name. A French name. You can see here that we've kind of given the regions names, right? And that's about as close as you'll get in RGB to giving every single color a name. So again, those of you who've played with color in Adobe products particularly, you'll have that RGB color value number thing where it's 0 to 10, 30. You'll see those three numbers: R equals 0, G equals 210, B equals 30. That's kind of how RGB colors are described typically. So different color spaces, and this is a really poor illustration, but just to give you an idea that the colorimetry or the color space of film on the left at the time of this illustration, which was showing standard definition TV on the right, was more. So film had more color sensitivity than television, right? Nowadays, it's probably switching the other way. As we go to 4K, 8K, we get more and more color spaces available, wider color spaces. Another term to describe the subset of colors is the gamut. So just to be confusing, the color space can also be referred to as the gamut. It means a slightly different things. The color space is, if you will, how do you describe this? Did I describe it in here? Yeah, here we go. Good, I thought of this already. I should know this. Yeah, the color space and the gamut are different things, different names for the same thing in a way. It's just basically how you apply them. So here's my illustration how you apply it. If you think of the color space as the area of color, like that triangle that we had, and the gamut is really the ability of a device to show those colors, right? I know, just like my friend here, you're probably a little bit confused. So the color space is the actual area on the diagram. That actual triangle you saw back here, these are the color spaces. The gamut, which is kind of the same thing, really refers to an equipment's ability to show a color. So you would say that, you wouldn't say, for example, that the Sony A7 camera has X color space, but you would say that the Sony X7 camera has 2020 color gamut or Rec 709 gamut, right? It's really the property of the equipment as opposed to the actual space. All right. So another definition of gamut is the range of colors possible by mixing three colors in varying hue and saturation. And it's the subset of colors like color space, right? But it's always tied to equipment, pretty much. Different gamuts, yeah. So just a quick illustration of CMYK, you'll notice it's not a triangle because there's not just three primaries, right? And yet RGB is three, red, green, blue. So each corner of the RGB triangle touches, there's red, there's green, there's blue, right? Yeah, so just remember gamut. If you're confused about gamut and color space, gamut is usually defined by the equipment. You would refer to here. Let me think. Here, I just thought of this. Let me try this on you. So I like using car metaphors. A car. Yeah. So when you talk about how fast a car goes, you use that term fast. But when you talk about the speed, you're not talking about the car anymore, right? You're talking about the speed. So the speed is 80 kilometers an hour. How fast did the car go? 80 kilometers an hour. Same answer, right? So gamut's kind of the same thing. If you think of gamut as this, how fast, if you term it in that in your mind, how you know, this is not a proper way to use this, but I'll use it in a sentence. How gamut is that printer? Now that's not correct. You'd never say it that way, but that's not what color space does a printer have? How gamut, right? So what's the gamut of that printer? It's you know, Rec 709, which is turns out to be the color space for HD television. That's really handy that the printer and the color television have the same color space. Then the stuff you print will look like the screen, right? That's why you want to know these things. So if you're going to print something on a piece of paper, you might want to use that Rec 709 color gamut to get that same effect. Okay, so color space is kind of the absolute shape, and the gamut is the equipment's ability to deliver that shape, if that makes any sense. Yeah, and I've just said that. So color spaces tend to be named in video standards for video. Color spaces for CMYK have other names, and we won't get into those. But color spaces for video are things like Rec 709, which is standard def, and Rec 2020, which is HD/4K. And all those are the size of the triangles. And I don't know if I have an example. I don't. We'll talk about those later in the term, but recognize, if you want to Google it, you can see the Rec 2020 color space looks like one size of triangle, and the Rec 709 is a smaller triangle. It's an earlier standard, and therefore has fewer colors available, right? So what's important about this for you as professionals is that when you shoot in a color like HD color space, like a Rec 2020, and you project in standard def, you're going to automatically lose a lot of those colors. Standard def just cannot reproduce them because they don't exist in the standard def Rec 707 or 709 standard, right? So keep that in mind as well. And we'll talk more about that later on this term a little bit.